Okay, welcome everyone to the Tartan planning series. We've had some amazing speakers so far covering various aspects of planning for robotics. If you're new to the series, please check out our website, which is linked in the YouTube video description, to see the previous and future speakers. But today we're excited to hear from Professor Markus Ryll. Markus is a professor at the Department of Aerospace and Geodesy at the Technical University of Munich, where he directs the Autonomous Aerial Systems Group. Furthermore, he is the leader of the robotics sector of the Munich Institute of Robotics and Machine Intelligence. His research interests lie at the intersection of robotics, control, perception, and manipulation, with the goal of enhancing the autonomy, agility, efficacy, and robustness of aerial robotics with interactions with the real world. After a PhD at the Max Planck Institute for Biological Cybernetics from 2014 to 2017, he was a postdoctoral researcher in the Robotics and Interactions Group under the supervision of Antonio Franchi. From 2018 to 2020, he joined the Robust Perception Group led by Nicholas Roy at the Computer Science and Artificial Intelligence Laboratory of Massachusetts Institute of Technology. He has co-authored 36 conference and journal papers on top-tier robotics conference venues. His contributions have been accompanied by additional services to the robotics community, such as reviewing renowned journal and conference papers, organizing workshops in RSS and IROS, or serving as an associate editor and member of the award committee in ICRA. Thank you, Professor Ryll, for taking the time to speak to us, and the time's now yours.
Thank you so much. It's really a big pleasure to be part here today. Today I'm going to talk about path and trajectory planning for autonomous agents, and I just quickly, let me change the screen so I can click forward. Yes. I prepared a short content slide for you. So I'll skip the introduction part because I was just introduced, and then I'll talk a little bit about the motivation, why we do the research that we're doing in my group and what we aim for. And then I'll talk about 3 different projects. So basically 2 will be in the domain of navigation in constraints environments for UAVs. And then I'll talk about a recent accepted paper that's called Neural MPC. And then we'll have time for discussions. So let me quickly skip the biography. So thanks again for just introducing me here. And let's just directly jump to the research that we're doing in my group. So we structured the research that we're doing into 3 different main pillars that you see here. So the first one is here on autonomous flying, and all the talks or the topics I'm going to present today are in this domain. So the overall goal of autonomous flying is to fly with microaerial vehicles as fast as possible in unknown and potentially cluttered environments. And for example, a motivation why I want to do that are typically search and rescue scenarios. But then as well, we do research in the field of aerial manipulation. So what you can do, or you can imagine what we're aiming here for, is to do grasping and transportation tasks, but as well really doing direct object manipulation. And typical scenarios are direct human-robot interaction, but as well in this field of research, we as well investigate like unconventional aerial systems. That's the one that you see here. I hope you can see my mouse. So this is, for example, a hybrid aerial vehicle that combines soft robotics with conventional control of UAVs. And then as well, everything that we learned in the first 2 pillars, and we apply on larger scale systems that basically require a very different set of safety constraints. This is due to the case that these kind of platforms are really in the restricted airspace and therefore have to follow all the regulations for restricted airspace. So let's go into the field of aerial robotics. So aerial robotics is a growing field of research, and the task that we are going to tackle and why we actually want to do that is a typical scenario that we tackle are, for example, the maintenance of broadcast towers, or the maintenance of power lines, as well as construction sites that are arbitrarily far away or remotely located, and as well the typical case of industrial climbers that have to as well maintain wind turbines. So all these problems, or the subset or the common sense of these problems, is that these kind of tasks are first of all dangerous for human beings, and as well at the same time expensive, because either you have to employ industrial climbers to solve this task, or you have to use helicopters, or you have to set up scaffolding, which takes time and is well expensive. And to motivate that a little bit more, I brought you a video today, and I hope you can see that. Otherwise, you could try to look it up on YouTube as well. You'll find it there as well. So what is conducted here, and I'll just stop from time to time to explain it a little bit better, but I hope you can see it sufficiently well, is the maintenance of power lines. And in order to do that, there are basically two different options. So you can do the maintenance of a power line either by an industrial climber coming from the bottom. But in order to do that, what you have to do is to switch off the power line, because the risk is too high that you ground the power line through the climber. That would basically cause an electric shock to the climber. The other option to do that is leveraging helicopters, as you see that hopefully in the video. So what you see here, there is an industrial climber sitting on the landing gear of the helicopter or on a designated spot underneath it. And the industrial climber is flown to the power lines. And the task of the industrial climber is to actually climb on the power lines towards the power towers and check the isolators. And that is, first of all, a very expensive task, but as well, that's a very tedious task and a dangerous task. So there are as well several fatalities per year in this kind of a task. And let me quickly jump a little bit forward so you see what is actually happening then. So you will see that the industrial climber is putting a safety harness around. Oh, we just jumped a little bit too forward. Putting a safety harness on the power lines and then crawling slowly towards the power tower to check the isolators. And you can see as well on the parallel side, on the opposite side, there's a second industrial climber that is checking the other side. And you can imagine that this is a very tedious and as well a very dangerous task. So what we foresee on the long run for my group is to actually do this task with aerial robots. And what we foresee are robots that are really having dual manipulators in order to do this task. But to do that, there are plenty of challenges that have to be solved before this is possible. And in the next two slides, I try to summarize for you the three main challenges that I see in the domain of aerial robotics. And what I'm going to do in the next few minutes is discuss the differences and the challenges of aerial robotics compared to the typical case of a ground robot. So let's start with the problem that we are actually working with a floating base. So that's the first, or I try to summarize the challenges under the topic of a floating base. So you all know if we have a quadrotor, right, that flies, we have to directly compensate any applied wrench to the system. So if you think about a ground robot, right, you can just pull the brakes, and if you push it, the system will not move. But for an aerial robot, as soon as it experiences any wrench that is applied to the system, you have to directly compensate that. Otherwise, it will quickly drift off from a desired position or orientation. Then secondly, on flying robots, we have a significantly higher or a more inaccurate positioning. And this is related, first of all, to the nature that we move in 3D, but as well due to the fact that our system is always vibrating and drifting. So we cannot like stop and check for a long while or trying to estimate our position or pose for a long while, but we're always drifting. So that as well generates in average a higher inaccurate positioning. And last but not least, and therefore I brought you here this picture, if you really want to do aerial manipulation, you have to have some kind of an actuator on board. And let me quickly maybe change here to the pen so I can just highlight a few things. So you can easily imagine if we have here this arm underneath it, and let me draw here the arm. If we try to move this arm, we apply a torque with the motors. Right, so we apply probably around this motor here a torque, and what this will cause is following axial equals reaxial, and torque that is opposed in the opposite direction and starting to tilt our platform. And this is something we have to directly and actively compensate, because otherwise, you know, as well, as soon as we apply a torque, our platform will start to change its orientation or its attitude, and as well will start to drift away. And that makes the overall control significantly harder than for a ground robot. And for a ground robot, we can again pull just the brakes, and usually as well for a ground robot, the ratio between the mass and the inertia of a manipulator is significantly smaller than for a flying system. Then secondly, we have the challenge of an aerodynamic actuation. And this as well causes at least two problems. So first of all, the one that I like to call an additional dynamical layer is something that people usually do not think about. So again, if you think about if you take a ground robot, what you in the very end control, usually you don't have direct access to that, but what you can control in the very end is the current in the motor. And the current in the motor is somehow proportional to the acceleration of your wheel of a ground robot, right? And then you can integrate, if you at least think about it in a most simple way, if you have just like the one-dimensional robot, you can integrate this acceleration to the velocity, and probably the quantity that you in the end want to control is the position. So basically, you can just integrate the acceleration twice and you get your goal, the desired position. This is different if you think about a quadrotor. Why is this the case? So again, what we can in the very end control, or what we can assume that we can control, is the current in the motor. And again, as well, the current in the motor, as we see it here, like for this motor propeller combination, is proportional to the acceleration of our propeller. If we integrate now the acceleration of our propeller, we get the velocity, the spinning velocity of the propeller. But only the spinning velocity of the propeller is then proportional to the torque that we apply to our quadrotor, or to the thrust that we apply to our quadrotor. So we have at least one level of integration more than for a ground robot. And additionally, this mapping is extremely nonlinear. So the dynamics that are happening underneath the propeller is highly nonlinear. And as well, this brings us secondly to these problems of unmodeled aerodynamic effects. So this is a problem that usually occurs if you try either to fly very aggressively or very dynamically, or if you really do physical aerial interaction. So if you just want to, for example, use your drone to do some kind of an observance task, not with extremely high velocities, or if you just try to hover, these effects are not very dominant. But as soon as you fly very aggressively, you have to take into account these unmodeled aerodynamic effects. And this is very challenging. So first of all, trying to solve the Navier-Stokes equations that are modeling what is happening underneath the propeller is something that is extremely cost intensive. So for a modeling purpose, you could try to do that. But again, this will be something that is usually not possible in real time. But even worse, to solve that for a real closed loop controller, you would have to have knowledge of the full states of the disturbances underneath the propeller. And that's something that is impossible. So therefore, properly modeling in the sense of using it in a feed-forward control, these aerodynamic effects, is basically impossible. So this brings us to the problem that, for example, in the task of very aggressive flying, you have to come up with a potential idea to solve or to model these aerodynamic effects without leveraging Navier-Stokes equations. And then the third challenge that I see is the problem of having as lightweight platform as possible. And this causes as well several additional challenges. So if you really think about the domain of aerophysical interaction, that usually means that our end effector has to be built as lightweight as possible. And that usually causes that we're, first of all, using very weak motors. And as well, we build a structure that is very lightweight or very hollow. And that causes, first of all, usually vibrations of the end effector. And additionally, it causes, due to this lightweight structure, a lot of unknown non-linearities in the behavior of the end effector. And that is a challenge to use for a proper physical interaction. Then secondly, our perception is very limited, especially, for example, compared to other autonomous agents, like, for example, autonomous cars, due to the fact that we have to use lightweight sensors and a minimum set of sensors. So the most typical scenario on board of a UAV is that you have an IMU on board, plus one additional sensor that tells you something about your pose. This can, for example, be a set of cameras, or just a monocular camera, or a LiDAR. But usually you have just one set of sensors, and as well, there are usually small sensors and of smaller cost. So as well, the quality of these sensors is limited. And then last but not least, we have a very limited computational power on board. So that forces us to use simpler algorithms than we are, for example, used in autonomous cars. And we usually have to decide whether we want to have a CPU on board or a GPU. And both is usually some kind of an edge device. So as well, with a limited resource. Okay, so coming from here, from these challenges, let's talk now about autonomous navigation in unknown environments. And what I'm going to start with is are some results that are still from my time at MIT, where we developed this platform that you see here. And we're as well leveraging the same platform now in my group here at TU Munich for our autonomous exploration. So let me tell you first a little bit about the specifics of this platform. So first of all, this is a rather small scale platform, and it has more or less the dynamics of a flying fridge. So it is a very small platform with a heavy computer on board, which relates to the fact that as well, the flight time of the system is only about 8 minutes. So the weight of the platform is approximately 2 kilograms, and the size is approximately 35 centimeters. Maybe as well regarding the compute that we have here actually on board, this is underneath that you see here, this black and white box underneath the drone is an Intel NUC with an i7 Intel processor. The main sensor for this platform is an Intel RealSense D435 RGBD camera. So I guess most of you are familiar with this camera, but for those who are not familiar with this camera, what we see here on board, first of all, is in the center is an RGB camera plus 2 infrared cameras on the sides. And these infrared cameras are used for stereo vision, and that they provide an additional depth of the environment. Maybe as well, an interesting side note on that, this camera is really an amazing tool, and it's sadly discontinued. But just for some information, so the depth perception that is reliable if you fly outdoors is approximately 10 meters. So depending on the lightning conditions, this can be sometimes a little bit more, up to 15 meters. But as well, let's say like the really reliable depth perception is in the range of 10 meters. And if you really want to fly fast in this with an autonomous platform, for example, in the range of 15 meters per second, right? A depth perception of 10 meters is very limited. So basically, what I'm going to talk about in the next like 10 minutes is how we actually leveraged and how we designed the control algorithm to fly with this very limited depth perception, still with a velocity of up to 15 meters per second. Let me go to the capabilities of this platform. So overall, this platform was, and the software stack associated with it was aimed at enabling GPS-denied navigation. So we wanted to fly in an environment where we can't rely on GPS. That could be, for example, due to the fact that no GPS is available, for example, due to a tree canopy, or we want to as well move from an outdoors into an indoor scenario, or we could as well assume that the GPS is jammed in the environment we're flying. Then additionally, we want to fly fast in a cluttered environment and roughly at like an altitude of 3 to 4 meters. At the same time, what we want to do on board is object recognition. So for example, we had an object recognizer running on the platform that detects cars, people, door, and so on. And we want to as well localize those objects. Additionally, we want to do really a fully autonomous exploration of the unknown environment, create while we're flying a dense 3D occupancy grid of the environment, enable visual semantic segmentation. So as well, we showed that we can, for example, leverage classes of the underneath ground for the trajectory planning stack. So for example, we segmented roads and other classes of the environment. And last but not least, we basically as well implemented a waypoint navigation. So let's stop all this talking about the platform and let me show you a video with some experimental results. So first of all, what you see here is the typical ARVIS environment. With highlighted here or here in the center, highlighted the actual representation of the environment with an overview image from Google Maps. What you see as well additionally here is the starting location. That is marked here in the bottom as well. The drone starts here in the bottom point. And the task of the drone now is to autonomously navigate to certain waypoints that are referenced with the starting location. So for example, the first waypoint is the one that you see here in the top. It was just like 200 meters in front of the drone. Additional waypoints will be behind those buildings that you see here in the top right corner. And in order to get there, the drone will have to find autonomously a small pathway between these two buildings that you see here in the top. Apart from this, additionally, the drone is actually programmed to be curious about cars. So as soon as the drone sees a car, it will approach the car and map it in this visualization of the environment that you see here. What you see as well on board here on the left side in this grayscale image here is actually the object detector. And for clarity, we have as well here in the lower left corner, the RGB image of the camera of the drone. So let's get started. So we'll directly see that the drone is taking off and first of all, heading towards the next waypoint, but then starts to detect the first car. So it deviates from the original flight path. And then as soon as it has mapped the car, it continues with the waypoint navigation. You as well see now at the car or the drone reached the first waypoint and then detected again a car and now continued to follow the waypoint navigation. So let's wait a second until the drone now navigates to the small corridor. So you see so far the drone with a very limited perception in this voxel grid representation so far has not detected these two buildings that you see here. You will see in this voxel grid representation in a few seconds, these two buildings will pop up, and then the drone will start to navigate through the dense corridor, or the tight corridor here. So maybe a few words with respect to the corridor. So the buildings were approximately 1.5 meters away from each other. So that leaves a navigational space between these two buildings, given that the drone is from propeller to propeller, approximately 50 centimeters wide, just a range of 50 centimeters on both sides. So we had to very tightly navigate through this environment. What you as well see from time to time in the voxel representation that there's some kind of a salt and pepper noise that is just hallucinated by the Ryll sense. So maybe as well a few words on the actual navigation stack. So what I've written you in the beginning is basically what we do on board for the navigation is visual inertial odometry. So there is no real loop closure in the background happening, but the visual inertial odometry framework that we used here was just basically in the end off-the-shelf VIO framework with approximately a drift of 0.5%. So that means basically over a flight distance of 100 meters, we are drifting about 50 centimeters, which was sufficiently good for the planning that we aimed here. And you will see basically the last waypoint is flying back to the initial location. You will see that we very approximate or very precisely land at the same spot where we took off. So the overall flight path that you see or saw here now was approximately 600 meters long. And you saw that we managed to do that in a very fast time. So telling us that we flew partially with a velocity of approximately 15 meters per second. So let me talk a little bit about the actual problem that we try to tackle here. So as I already said, the challenge in this work was to overcome the problem of the very short-sightedness of the actual drone. So we only see 10 meters far. So what we have to create was a trajectory planner that is able to very aggressively replan the trajectory. So summarizing that, we want to build an online planner that can work in GPS-denied environments and in unknown and cluttered environments, but the planner must be able to react very quickly to new foreseen obstacles in the way. And basically, in the end, we seek to find a very smooth, high-speed, collision-free, and dynamically feasible 3D trajectory generator. So let me show you how we did that for this project. And in the end, this project and the motion planner was very highly successful. So in the end, we did approximately, I think, 5 to 6 hours of flight time with only having one real crash due to illumination issue. So the Ryll sense in the end didn't see an obstacle in the way, but we successfully flew distances over 20 kilometers with this planner. Let me quickly summarize how the planner works, and we'll just do that by going through the plot that you see here on the right. You can directly see by these two colors that we have two different control frameworks or control rates of this problem. One is the inner core that only runs with 2 hertz, and an outer core that runs with 30 hertz. And the 30 hertz control framework or trajectory planning path is basically triggered by every new depth image that we get from the RGBD Ryll sense camera. So let's start with a new sensor image that arrives. So first of all, this sensor image is fused to the inner core that generates the occupancy grid that you already saw now in the video before. And of course, building such an occupancy grid requires multiple depth sensor estimations. And this is, well, one of the reasons why we actually had to run this inner core at a lower frequency. Additionally, to this occupancy grid, we built the distance grid towards a local goal that we want to achieve. Importantly, the occupancy grid and as well the distance grid is in this framework implemented as a rolling buffer map. So you see a visualization of this rolling buffer map, so basically of the occupancy grid here in the center. And the size of this occupancy grid is 60 by 60 meters with a height of 6 meters. with the quadrotor in the center. So that means basically as soon as our quadrotor starts to move in one direction, it will forget about things that are in the past in the background of the drone and learn new image features or environment features on the new observed space at the end of this occupancy grid. So the reason why we implemented that in this way was to achieve a global path replanning rate of 2 Hertz. But of course, with the cost, so the larger we would make it, the planning would take longer. But with the drawback, if we make it smaller, that we might end up in a dead end that is larger than the size of the grid map. So we fused then the occupancy grid with the distance grid. And again, the distance grid tells us the local goal where we want to fly to a cost grid. And in this cost grid, we basically planned a path, a global path towards the local goal. So for example, to the next waypoint. And this global path planning is basically just built on top of Dijkstra's path. So nothing that is really very fancy. And on top of this global path, we now ran a running carrot, which is our local goal for the trajectory planner. So you see here already, this is like the typical scenario that is done very commonly in trajectory planning for very dynamic systems, that we split this problem into a path planning step, right? So where we just get a path that it doesn't have any time information with it, but just like a feasible solution to get from our current location towards the goal location. And then additionally, the second step is to compute a trajectory planner or to find a trajectory that we want to track. And this brings us to the outer loop. So the outer loop really runs with every new depth image and runs with 30 Hertz. So the first step that we do is, again, fusing our depth sensor to a voxel grid representation that contains only the latest depth information. And this voxel grid is then fused into a KD tree representation. What is the benefit of it? So a KD tree representation allows you to very efficiently search for collisions. This brings us now to the third block here on the right side. So what we do as well with every new depth sensor estimation is creating a set of motion primitives. So this set of motion primitives is not computed once in the beginning, but it is computed at every arrival of a new depth sensor measurement. And this motion primitives, you have to imagine them. They basically start with the state of the robot at the moment of the depth image arrival. And what we compute then is a huge set of different motions based on polynomial trajectories. So that's something as well that is very commonly done for trajectory planning for quadrotors. The reason why we use polynomial trajectories is that polynomial trajectories, due to the flatness of quadrotors, they can be very efficiently checked for dynamic feasibility of these trajectories. So what we do, we achieve or get a new depth image, and we compute a set of motion primitives, and the set had approximately the size of 700 different trajectories. And you have to imagine them, these kind of trajectories, they start at the current state of the quadrotor and go like spaghettis in all kind of directions. So for example, some of these tracks just moved forward, or of these paths or trajectories, some of them just like turned the drone around. Others just tried to immediately stop the drone. Some went upstairs or downwards. So really like a large set exploring all the feasible state in the current environment. And then we evaluated this very large set of motion primitives, first of all, with respect to dynamic feasibility of the quadrotor. We evaluated them against collisions in our KD tree, but as well, for example, we evaluated them on proximity to the KD tree. So are there some trajectories that are very close to obstacles in the environment? And then last but not least, we evaluated them against a running carrot on our global path. And this running carrot on the global path was was basically represented by its own state. So this running carrot had its own state and was moving fast in very cluttered free environments, but moved very slowly in very cluttered environments. And with that, basically as well, had some kind of a gas pedal that allowed us to control the drone very slowly in very cluttered environments and to really fly fast in very clutter-free environments. And after this evaluation, we just selected the motion primitive with the highest score and followed this motion primitives and waited till the next depth image arrived. And you can easily imagine with this approach, we actually never followed a motion primitive to its end, right? So some of these motion primitives were really long, like 30 meters long into the future. And to follow them would, at least if we fly with 15 meters per second, like need approximately 2 seconds. But we only followed a first step of this motion primitives until a new depth image arrived, and then we started this computation again. So this was in principle very successful, but again, it has the drawback of splitting the problem of trajectory planning into 2 different steps. First, as well, we do a path planning step, and then afterwards we do a trajectory planning step. This has a fundamental problem or a fundamental drawback. Even if you find an optimal path and an optimal trajectory, which is, for example, with this machinery that I just presented, actually not the case, right? So we did not find or try to plan an optimal trajectory. Even if you find for both cases an optimal solution, it is not given that the combined solution is the optimal solution for the problem. And that brings us to the second part of this talk on motion planning. And this is based on path parametric motion planning. And let me go back a step and motivate path parametric motion planning. So why do we do that in general? So motion planning is a very appealing problem and still an unsolved problem. So motion planning is a key ingredient for the industrial revolution, but as well used, for example, for CNC machines. So it's as well a key ingredient to allow high precise manufacturing. It is used in multi-robot scenarios. So like, for example, in fulfillment centers like the Amazon warehouses. It's as well used for robotic planning in medicine, as well for leveraged in controlling satellites and space missions. And of course, it's a key ingredient for having autonomous platforms, for example, in remote areas. But let's again go one step back. And what is actually motion planning? And here I just really brought you a toy example. So what we're talking about in general is some kind of an agent, right? And this agent has some kind of dynamics, and it has as well some kind of dynamic constraints. And the goal of motion planning is to bring this agent to a goal state, right? And this goal state can be, for example, defined in position and the twist of the system, so the current velocity and the translational and the rotational velocity, but the solution is shaped by the environment in between. And what the actual cost to go is, or the problem that you want to optimize, depends on the task at hand. So what you, for example, can try to do is building a fast robot or an efficient robot, or you could actually try to find the solution in the environmental motion planning, which gives you the shortest path to the goal. But this is not the only problem that we have to tackle. We actually have as well the problem that we have to consider, for example, that we have very different kind of agents in the environment. So it might be that we have this very big robot that first of all has different kinematic constraints, but as well different kinetic constraints. So for example, it might be the case that for this kind of a robot, we have to find a very spacious path to the goal. So we see that this motion planning depends on, first of all, the environment, but as well on the agent itself. So, but is motion planning solved yet? Or is it something that we still fight with? And in order to understand that better, I just brought you 2 examples why motion planning is actually a discipline that iterates with every other progress in the field. So one thing that changes constantly is the hardware where we can apply our motion planning. Just to give you here 2 examples, we have here, for example, the Boston Dynamic robot, or one of these very agile drones. And with the increased agility of platforms, the problem becomes more challenging, right? So first of all, we have to, or our platforms in general become more agile, which challenges the motion planning. But additionally, the control loops getting faster and faster, which as well challenges the problem of motion planning, especially motion planning online. And then additionally, computer vision and sensor fusion is getting better over time. So that results in a more fine-grained resolution of the environment. So a representation of the environment becomes more fine-grained, allowing us to better exploit the free space of the environment. But even more interesting, we as well get better in semantic scene understanding, which allows us, for example, to map our environment in different classes. But even more important, we can, for example, detect other agents in the environment. And suddenly we're not planning in an environment anymore that is static, but we plan in a dynamic environment where we know that other agents have specific properties and physical properties as well. And for example, it is important to avoid or fly by next to a car differently than we fly by next to a human being. Okay, so the overall motivation and research question that we asked ourselves is, can we, given an agent and a constrained environment and some performance criterion? And again, the performance criterion that we are tackling here is, for example, finding the fastest path or the most efficient path, formulate a motion planner that is, first of all, capable of directly computing the optimal motion, then obeying the environment's geometric properties and the agent's physical limits, while being applicable to any dynamical system, fulfill the constraints of the system, and this is most important, to run everything in real time. So basically, this can be summarized in: we want to be optimal, we want to be universal, safe, and efficient. And efficient here in the sense of being efficient computation-wise. So this brings us now to path parametric control. And let me start here with a simple example. So imagine that we are controlling this car here that you see here, and we want to control this car, or we are in the scenario of doing some kind of a racing, right? So if we do racing, what we can actually exploit is the full space of the road, right? And let's assume now there's, even for this toy example, not any other car driving on this road, but we can exploit the full space of this road. So what you actually could, for example, do is just trying to track this red path that you see here. But for a racing scenario, you can easily imagine that this would definitely not be the optimal scenario. So what we're going to do now is to reformulate this problem with respect to a parametric path. And let me show you what that means. So what we actually represent now is representing the street that you saw here with the center line initially as a parametric path. And we consider our system here just as a dynamic system, okay? And we can describe this parametric path with certain different features. So this method assumes that the geometric path of interest is given by a function that maps the path parameter to the three-dimensional coordinates. So during this presentation, this mapping will be denoted as gamma, that you see here, while the path parameter will be psi, so the psi you see here. And we can as well, in a second step now, exploit or represent our dynamical system with respect to the path parameters. Okay, so this is the actual interesting change that we do. So we describe the dynamics of our system, not in Euclidean space anymore, but with respect to the path parameters. Why is this great? So let's go one step back and think again about the problem. So if we go back to our description of the road, so the overall goal where we're aiming at is describing our problem in a way that we can optimally exploit model predictive control. And in model predictive control, you usually set your boundaries, for example, to express the boundaries of the road. But this is not formulated in an optimal way for model predictive control. But what we're doing now is expressing the dynamics of our system with respect to the path parameter and including directly in the formulation of the problem, the space that can be exploited, for example, just by the distance from our path with respect to the end of the road. And that makes the full formulation of the problem very efficiently for motion planning using model predictive control. So let me jump directly forward to the first problem that we tackled. So again, we just said that what we want to do is expressing our Euler coordinates in spatial coordinates. And one approach that has been tackled already in the past, and we tried in a very first step as well, is leveraging a frame that's called the Frenette-Serret frame. And that has as well been exploited as well in the past by other people. And the goal for this project that we wanted to do here is leveraging the Frenette-Serret based frame for a racing scenario of a quadrotor. So basically what we did is formulating the dynamics of the system with respect to our path that you see here in the center. And basically as well, the dynamics of the system are represented as or with respect to our path. Let me show you a video of this results. And again, here the goal of this was to do drone racing. Let me quickly pause it so we can fully understand it. So what you see here with this yellow curve is our approach, and we compare it to a time optimal solution that took hours to compute. But our approach is really calculated in real time to control the drone that you see here in a simulation. And we defined our spatial constraints in a way that we gave lots of slack for spaces where there's no constraint. And if you know this drone racing scenarios, the goal is usually to fly through certain gates. And you will see that in the spaces where there is a gate in this racing scenario, and this is basically just following the alpha pilot challenge, you will see that this gate is, or this free space is shrinked to the size of the gate to fly through. Let me pause here. So basically, for example, you see here the visualization of the gate, and the next gate is something that you can see here. And this red line is the prediction of the nonlinear MPC that was solved while flying this trajectory. So you can see that our solution actually finds a solution that is very close to the time optimal solution. Of course, we do not achieve a time optimal solution because the time optimal solution takes hours to compute, but we get really close to that. So starting from here with this reformulation of spatial coordinates, we as well realized that there are some limitations to the Frenet-Serret-based frame. And this brought us to the next topic. So let's quickly have again a look to the Frenet-Serret-based frame so we can express that, the Serret-Frenet-based frame, as you see it here, with the coordinates that are depending on our path description. And just to explain that, so basically what we see here with the bar is the first of all the derivative with respect to the coordinates of the path. And here we see the expression of the Frenet-Serret-based frame. So basically, the Frenet-Serret-based frame gives us directly torsion and the curvature of the frame. And this results in a very simple analytic representation of this path, but it comes with a cost. If you want to combine multiple paths exploiting the Frenet-Serret-based frame, you have in the point of the conjunction of two of these curves a nonlinearity or a singularity. Why is this the reason? So if you take a look again to the description of the Frenet-Serret-based frame, the y-axis of the frame always indicates to a certain direction. And that causes that, or into the curve or the radius of the curve of this path segments. And this causes a nonlinearity or a singularity in the point of combining two different frames. This is the first drawback of the Frenet-Serret-based frame. But additionally, if you take a look to the orientation of this frame, you see that there is an undesired twist, which usually causes, if you want to track exactly this frame, which causes the system to require more energy than it's actually needed. So doing some kind of literature research, we found that there are as well rotation minimizing frames. And this is a definitely better solution, but it's as well at the same time a more complex solution. So let's take a look into different rotation minimizing frames and how they're expressed. So the question that we asked there again is now, is it possible now to formulate a singularity-free, continuous, and twist-free spatial representation or reformulation of the Euler coordinates by relying on an exact formulation and a compact representation of the environment? So this was the research motivation that we asked ourselves to come up with a better representation than the Serret-Frenet-based frame. And actually, what does this compile? So first of all, it shall be compatible with optimization algorithms. It should be a smooth environment. And last but not least, no approximations and few coefficients. So resulting again in computational efficiency. So the first step that we did is basically, again, just doing the math to express our system dynamics with respect to a moving target on a path. And what we ended up finding is something that is called Pythagorean hodograph curves. So Pythagorean hodograph curves are curves that are highly used, for example, in the field of computer graphics. And basically what they are bringing is Pythagorean hodograph curves are very efficient and continuously defined functions. So pH, or I'll from now on call Pythagorean hodograph curves just due to the long name pH curves. So pH curves are a subset of polynomial curves whose parametric speed is the polynomial of the path parameter. Or more specifically, the path parametric functions are related to 4 polynomials, you see that here, which can be collocated under quaternion polynomials. So what does this bring us? So we can just formalize this all now with Bernstein coefficients, but this brings us, in other words, curves of an arbitrary degree, and we can choose this degree by selecting the polynomial order of these functions with a very high efficiency, or with choosing the order of the polynomials as we would like to have them, with the fact that we have 4 times n plus 1 coefficients. But with that, we have suddenly an extremely powerful tool to express any arbitrary curves in a given environment. And let me bring this now here a little bit to an end. So how did we formalize our problem? We first expressed the dynamics now with respect to pH curves of an arbitrary system, and then defined our Pythagorean hodograph curves. And we leverage this now in an MPC control framework again, which brings us enhanced spatial awareness in motion planning. Let me show you now the results of that. So the overall idea is the first one. So first of all, we assume that we have some kind of a free space, and we assume that this free space is given. For example, it is given by just like perceiving the environment. So again, imagine we have a system where we have a depth sensor and we can observe what is the free space, and we plan to the end of this free space. And then we do in the second step, we compute our pH spline in this environment. This gives us the formulation for the NMPC, for the Model Predictive Control. And finally, we compute the NMPC based on the pH spline. Let me show you some experimental results. So what we first started with this rather complex environment with a start point and an end point. And then we fitted into this some kind of a representation of the free space that you see here highlighted in blue. And then built into this free space, we found our pH curves. So maybe one step back again. So what is important to understand here is that we use the pH curves only to represent the free space environment. So it is not the goal to actually try to track those pH curves, but we leverage the representation of the dynamics with respect to the pH curves to formulate now an MPC problem that can be solved very efficiently. As in the MPC problem itself, we have the geometric description of the problem described inherently, and we can solve this problem very efficiently. So let me show you some results here. So what you see here, first of all, I hope that is big enough here in this representation of the environment of the free space with the coordinate frame, the found pH curve that passes through the environment. And once we feed it the problem through the MPC problem, you see a solution of tracking the desired trajectory in an optimal way now. And of course, we can now represent and take a look to the path parameters of the pH curve. But what is even more interesting, if we now take a look of the solution of the Model Predictive Control framework, we see that we, for example, in the acceleration, always reach the physical limits of the system. So let's conclude this topic now here for a moment. So actually what we achieved here is that we formulated a singularity-free planner that is continuous and twist-free, that allows for an exact representation of the environment and is very compact. So let's stop here this first part of the talk, and let's come shortly with a few minutes on the second part of the research that we're doing in my group. This is now on leveraging the deep learning in an MPC framework. So let's go one step back again, and let's talk about the problems that we have in flying autonomously this kind of platforms. So for example, drone racing. So we talked about that many of the effects that we see there are highly nonlinear, and especially the problems of the aerodynamics are extremely hard to model. And if we want to leverage model predictive control, right, and model predictive control is widely used in robotics, we have the problem that to do the rollout of the model predictive control is we have to leverage or rely on models that only rely on first principles. Otherwise, we would not be able to run an MPC framework in real time. On the other hand, we're having machine learning and especially deep learning, which is usually more used in the upper lab of, or the upper layer of robotics. So for example, in perception, so that means like in semantic classification and these kind of problems. And deep learning has the benefit that in the end, depending on the size of your model, you almost have an unlimited modeling capacity. So that means you can as well, in the end, pretty well learn the aerodynamics of a system. And what we've done now in the framework of Neural MPC, this paper, is combining both deep learning and MPC in a real-time approach. So let's quickly talk about real-time iteration and MPC. So how is this done? So first of all, we assume, or we have basically three different options. We can assume that the state does not change between two MPC time steps, or we could assume that the change does only vary slightly, so we would have to solve our problem in a sequential process. Or if we really have a high frequency that leads to small changes, and that is what is really usually done in real-time iteration, we only solve the problem in a single quadratic program, right? So this is the standard way to solve real-time MPC. What we have to as well accept in real-time MPC is that we solve the problem every time step and we basically just linearize it. So we assume that there's really only small changes. So of course, first of all, we're not now the first ones that want to run a large or a large learned model in a real-time framework. But how this is usually done is, first of all, offline, you collect your data, then you define your PyTorch model or whatever framework you would like to use, and you train a rather small model. And then you copy your weights to the model predictive control framework, compile the model predictive control framework, and then in the online approach, when you run your hardware, you first of all run the MPC with real-time iteration, and then you hope that due to the large framework use or the size of the framework, that everything is fast enough. So in our approach, in Neural MPC, this is now slightly different. So again, we first of all collect data offline, and we as well as before train our model. And now we can almost an arbitrary large network train and again compile the MPC problem, but not taking into account our trained model. But what we do, and that's different here, we run our MPC with the real-time iteration, and at each optimization cycle, we approximate our learned model as a first-order Taylor expansion. And this is something that is coming basically for free from the learning process, right? In the learning process, we as well have to do the Taylor expansion of our model, to compute the cost, and to do the backpropagation in our model. Let me show you one plot that shows you comparison between the so far state of the art and our approach. What you see here on the x-axis is the size of our model. So the neurons per layer, from very small models to very large models. And on the y-axis, you see the runtime of the algorithm. And we assume that to run such an algorithm in real time on a drone, you can either have basically two different benchmarks you want to achieve. So you could, for example, either run it like with 50 Hertz or with 100 Hertz. Now you see 6 different comparisons. The algorithms that we compare with are here highlighted in orange. So first of all, basically what we used here is running the model that you see here, pre-compiled as you've seen it in the first slide, and compare it to the runtime on different platforms. So first of all, we here in orange with the crosses, we run it on a naive ARM implementation. And as well here in orange, we run it on an i7 processor. The other part that we see here in blue is running our approach on a CPU architecture. So this could be an edge device as here seen on ARM, on this one, on an ARM processor, or on a really dedicated hardware, which is either a GPU RTX 3000 or a GPU Jetson processor. So what you see is, of course, if we have a very small scale network, then a naive implementation is faster. But as soon as we start to get to large scale networks, we see that our method outperforms significantly the naive implementation. So for example, even on edge devices, we can run our system at 100 Hertz on, for example, our GPU implementation. And on the GPU Jetson implementation, we can still run it of up to 50 Hertz with a layer size of 2 to the power of 12. And if we use a GPU RTX, we can really run very large models, even at a very high frequency. Let me show you for this 2 real-time experiments. So what we've been doing here is trying to just like fly with a quadrotor, first of all in a circle, and then within an H-shaped trajectory. And we increase the velocity of the quadrotor. So first of all, here it was just like the velocity that we increased over time. And let me as well bring this to an additional experiment. We now followed the H-shaped trajectory, and you see that we have an extremely fast changing dynamics of the system, and we quickly end up in the downwash of the propeller itself. So in order to learn the model, so we just flew this trajectory like 2 or 3 times to learn the model of the system. And then afterwards, the goal of the problem was to track as accurately as possible the actual H-shaped trajectory. And we could show that with this learned model, we could significantly better, so up to 60% better track the references than, for example, the state of the art using Gaussian processes. Another experiment that we conducted was the second step. We wanted to show that we can as well, for example, compensate the ground effect. So what we've been doing is just flying over a table, and as an input to the model, we just used a map of the environment. So just a 2D map telling us where is actually the table. And as well, let me quickly show you here the results. We could very accurately or significantly decrease the break or the increase of the system due to the ground effect. So basically what you see in blue is our approach, and in orange the baseline, again using Gaussian processes to model the behavior of the drone. You see that we track the desired constant altitude over the table significantly better than the baseline. Okay, this brings me already to an end of this talk. I know I took a little bit longer than expected. I just first of all want to thank all the people in my group that are collaborating with me. Of course, this was not done that I've done alone, but mostly the work of my PhD students. The work that I mainly presented today was the work of Tim Salzman, that's the work of the real-time MPC, and of John Arita-Balaga, who is working on the trajectory planning. And of course, this is well research collaboration with lots of groups. And now we have time for discussions and questions.
Yes, thank you so much for this wonderful talk. If you have any questions, you can go ahead and submit them on YouTube if you're on YouTube, or in the Q&A of Zoom, or if you're here on Zoom, you can just raise your hand. I guess I can start with one. So there were a lot of interesting applications that you presented for applications for UAVs, and a lot of these with like these high-speed trajectories. I was just wondering for you, what are some of the most exciting applications that you foresee, maybe that are coming to light the soonest, or that you've already seen?
So one of the biggest challenges that I foresee for the future for high-speed flying is really flying in dynamic environments. And that is something that is still unsolved. So really incorporating the dynamics of additional agents in the environment, predicting the behavior of this other agents in the environment into the future, and then reacting to, which almost ends in some kind of a gameplay of the behavior of your system and the agent. And this is something that is unsolved currently.
Thank you. Are there any other questions? I have one more if nobody else has one. Let me just double check. Okay, so another one I have, just kind of based on your just most recent work you presented, using deep learning within this, lower level controls at this point. What do you see or foresee as maybe the next steps in like the next 5 years as far as incorporating deep learning into this like either controls or planning framework?
So this has an interesting application or implication. There are, in the end, two options that you can do, right? One step is in the full framework of MPC or of machine learning is to really try to do an end-to-end learning for everything. And this has definitely benefits, and it especially has benefits if you aim at a very specific task. So if you, for example, know you want to fly in a warehouse and you have like constant and very well-known properties in this environment, and you can basically learn all the features in this environment, the end-to-end learning is probably the way where you will achieve the highest or the best results with respect to the task. If you aim more for a system that is more robust to broader spectrum of applications, where you would need a very, very huge set of data to cover all edge cases, and especially where you need certain safety constraints, I don't see another path than still breaking your system into specific subblocks and check for safety of every single subblock. This is something that we'll see in the future for a long while. I think this battle between like really end-to-end learning and still the breakup of problems into specific tasks that will be solved partially like with analytic approaches and partially with learned approaches.
All right, thank you. Thanks again for taking the time to speak to us. Have a good day.
Thank you so much.
Yeah.